Welcome to the NeurIPS 2024 tutorial on causality for large language models. I'm Jijing Jing, and my co-instructor is Sahil Garrido here. And we're from Max Planck Institute for Intelligent Systems, flying from Germany to here. I'm also an incoming assistant professor at the University of Toronto, joining next year. And Sahil is also a PhD at Amazon Research. We're both part of the ALICE program across Europe. So today's 2.5 hours tutorial will be composed of the following 3 components. The first one is on causal reasoning skills in LLMs, which we will cover why LLMs need to learn causality, some basics to introduce causality, and how the current LLMs handle them. The second part will be on causally understanding LLMs, where we will cover the necessity of LLM evaluation. And for black box LLMs, we will describe how to design causal behavioral tests. Then lastly, for white box LLMs, we will talk about interpretability by causal inference and causal representations. Lastly, we will have an exciting panel discussing what role will causality play in the future of LLMs. For the panel, we will have Joshua Bengel, Bernhard Schokopf, Swaroop, GB, Tom Everett joining us. And also before we start our tutorial, we really want to deliver a lot of great gratitude to people who have gave us feedback during many of the practice runs of this tutorial, especially from Amazon Research, Max Planck Institute, and many other places. And for people who want to keep a copy of what we have talked about today, feel free to also keep track of the GitHub paper list that we curated on causal NLP papers. Moreover, a previous edition of this tutorial for less about GPT and other LLMs, but more about how to use text embeddings to do causal inference is at EMNLP 2022. And then later, we plan to release the YouTube video or whatever format of this tutorial on X. So with this, we will dive into the first part on causal reasoning in LLMs. As many of us in this conference already know, the use of LLMs has been extended to many applications, such as for code generation, for robotics, decision making, computational social science, and many others. However, before all these applications, we do face a reliability problem. If we look at some error reports by users on some LLM models, we might see examples such as LLM suggesting gluing pizza and eating rocks. For the pizza example, the user put in the search query cheese not sticking to pizza, and then I guess this was some earlier version of it. It must have already been improved. So some earlier version of the model actually suggested to use some non-toxic glue and make the sauce more sticky to the pizza. And sometimes such error also come from wrong imitation. So this how many rocks should I eat example, when it's put into the search query, the AI generated overview actually mentioned a rock a day keeps the doctor away. And then actually it wasn't that crazy in that there was actually some websites mentioning the same thing. And apparently it means that the Onion website is not that scientifically reliable. So what happens when LLM receive a question, given all these motivations? Upon a receival of a text question, usually we can see 3 modes of how LLMs work. The first version, the earlier version as we can see in GPT-1, GPT-2, and similar models, we can usually trust it in generation, such as the capital of France is, and then waiting for it to generate Paris. The second mode could be using everything in the first mode plus retrieval augmented generation, RAG. So this is an example where LLM can perform a search query over the websites or over documents. Lastly, in the third mode, LLMs can also be connected with structured formal reasoning, where it can call code, call API to execute things. And each of these modes have its pros and cons. For example, the first mode, we will see such examples as gluing the pizza, which is a case of hallucination, namely LLM generating grammatically plausible answers, but semantically it doesn't make sense. For the second mode, we might face the problem of misinformation. So if there already exists websites also talk about this, which site should I trust and citing my answer? Lastly, at least me personally, I really trust this direction of LLMs with structured formal reasoning as a future way to make the outputs more solid and reliable. Just to see an example of how some current progress on this line has been. So we've done it very fresh, query today using ChatGPT 01. And I usually like to ask this question, what's the 17th root of 1,000? So it thought for 7 seconds. And the way it performs the answer is that it breaks it down to each of the steps, like express 1,000 in a simpler form, take the 17th root, and so on, before diving into the final result. So we can see that it has sort of a structured way of doing things, and also for each of the steps, if there needs to be a case of a pretty complicated calculation, there might be some API called in the backend to make sure that digits are correct. Bring this spirit forward, we further ask the question, do we also care about LLM functionalities besides math and fact-checking? And the answer is causality, which will be the topic of this.
So let me start with a very quick disclaimer. There are many different traditions of causality, like the potential outcome tradition of causality, Pearl's view of causality, Philip David view of causality. But we're going to focus on Pearl's view of causality, which is based on causal graphs and structural causal models. But before we go into the technicalities of structural causal graphs and structural causal models and graphs, let's have a motivating example from causality and statistics. So first, let's look at this figure in here. What this is showing is basically on the horizontal axis is the amount of consumption, let's say per capita, of chocolate per capita. And on the vertical axis is showing the number of Nobel Prize winners per 10 million population. And then we can all see that there is a very strong correlation between the two of them. But I think most people in here would realize that there is no causal connection between the two variables, or at least none of them is a cause of the other one. And the thing is that some of these analyses that have been done, they make it even to the news, maybe confectionerynews.com, but also all the way up to Forbes, and where even they make claims that sound a little bit causal. But obviously, we need better analysis than just correlational analysis, which is what we just saw in here. And then this is not only about these toy examples, let's say, but as Jijing has already explained, LLMs, they are very good at solving certain tasks, like some text generation, information retrieval, and even some maybe some simple math, but Jijing has also showed that it can fail whenever it wants to have a bit of this causal flavor. So this is pretty much what is missing at the moment. And the idea is that we don't only want to use whatever data was used, maybe let's say to train, but we also would like to do something that is a bit of out of distribution prediction, like maybe something like future prediction as opposed to just simply past data. In order to do this, we need to know basically what causes what. Okay, so now let's start a little bit with the technicality. We'll first start with some language of causal graphs, and then we'll introduce a little bit more of causality. So causal graph is a very simple mathematical object. We have these vertices, which represent causal variables, and directed arrows between these causal variables. This is called a directed graph, and in particular, we're going to assume that there directed acyclic graphs. So basically, there are not going to be cycles between any of the variables. And then we'll use this, let's say, family language to say that something is a cause of something else. So we say, for example, here below that X directly causes X, or X is a parent of Y, or Y is a child of X as well. These are all like equivalent ways of referring to this same relation between X and Y below. And this, what's coming here is probably one of the most basic concepts of causality. So the idea of causality is that we're going to have some form of true factorization of the data, or causal factorization of the data. We're going to assume that there is a factorization in conditional distributions of each one of the variables of our models, where we're going to condition each variable on its parents, on its causes, direct causes. And then because the product of conditional and marginal distributions, they produce the distribution of the data. So the whole distribution of the data, it's going to be the product of these causal mechanisms. We call independent causal mechanisms or causal conditionals. And notice that this is in contrast to any other possible factorization of the same data. Because if we have these four variables, X, Y, Z, and W, we can factorize them in different ways. But then whenever we assume that there is a causal graph, a true causal graph, then there is only one valid factorization for our joint distribution. Okay, so let me give you a bit of an example, because this might be a little bit abstract. So let's assume that we're looking at a model of how plants grow, and then this is our small causal model. So we're going to have maybe the growth of a plant, and the growth of a plant in this very basic model will depend on the water that we're giving the plant and the sun hours that it receives. And then these two variables, they're going to be dependent on the location where the plant is. And then above, with what we believe would be the true causal factorization, at least the one we're assuming in here. So we're going to say that the location has certain distribution, basically how plants are located across the earth. The rain is going to be a function of a location, sun or light is going to be a function of a location, and the growth is going to be a function of the rain and the sun, or light, water and the sun. And below, we have another valid factorization of this joint distribution. This is a valid distribution, but this is not the causal factorization. And so we see, for example, that the growth of a plant does not depend on anything, which is not what our intuition would tell us. Okay, and then let's look a little bit of code to see how would this look on our computers. There are several packages that do this. We're going to be looking at this is one of the examples. So then we can see here we have three variables. They correspond to the causal graph that we have in here. And this is simply three variables, and we can see that the location always depends on the variable above, which is precisely what we see on the causal graph. And then we can initialize a causal graph object in here, where we initialize also the edges between each one of the variables. Okay, but also we might be wondering here, why do we need graphs, right? We could simply use the factorization without the need of a graph. But then the interesting thing is that these graphs, if maybe an expert comes and writes down the graph for us without actually having to give us the conditional distributions that we want, they imply some testable assumptions. We can falsify causal graphs through the data. We can falsify graphs through the data. To do this, let's look at this concept of independence. And maybe you recall from your probability classes, then we have this thing called marginal independence. So this is basically two variables are independent if the joint distribution is equal to the product of the marginal distributions, or conditional independence is very similar. So the joint distribution conditioned on something else equals the product of the conditional distributions. And so here we have some examples with the graph that we have been looking at. We have that, for example, X and Y they're conditionally dependent given W. This W in this case is called a collider. We have that X and Y is independent of Z. It's called a confounder. But if we don't take into account Z, if we don't condition in Z, then X and Y are not going to be marginally independent. They're going to be marginally dependent. This is basically what we can falsify. This is what the graph is telling us, and we could go to the data and verify that, let's say, through some conditional independent tests. And more generally, we say there is this local causal Markov condition that says that any two variables on the graph are conditionally independent given the parents of variables. Let me repeat that. For any two variables, xi and xj, they're going to be independent, condition on the parents of I, as long as j is a non-descendant. And let's look at a particular example of this. So as we said before, x and y are conditionally independent given z. So x is a non-descendant of y, let's say, and if we condition on z, which is the only parent of x, they're going to be conditionally independent. And w and z, they're non-descendants, and z is a non-descendant of y. If we condition on both x and y, which are the parents of w, then they're going to be conditionally independent. Okay, so now let's talk about the two largest tasks in causality. The first big task in causality is whenever we know a system, whenever we have data on the system, and whenever we have a causal graph, can we say what happens to the joint distribution whenever we modify one of these individual mechanisms? And then the second big task of causality would be given a set of variables, so we get an Excel sheet or a pandas data frame without any graph. Can we make certain assumptions, or under which assumptions can we retrieve the causal graph that generated such data? And notice that in both cases, we are assuming that we have a notion of a variable. So we know which units on the data, they produce which unit of the data create a variable, as opposed, let's say, talking about images, where in images we have these values of the pixels, but it's very difficult to say what is actually a variable in there. Okay, so let's focus on the first task to begin with. So let's talk about this idea of intervention, which is also central to causality. So the idea of an intervention is that we are going to change one or more of the mechanisms that compose the causal graph, and because the causal factorization that we've been talking before, the joint distribution of all the data is also going to change. So for example, if we are going to intervene only on variable j below, then what we're doing is either changing the probability distribution of xj given its causes or its parents, or maybe we can also change the dependence in its own parents as well. And then the joint distribution is going to be simply the product of all of the causal conditionals as we have seen before, but we're going to exclude that j variable and simply the new modified or intervened mechanism in there. And so the way that we think about it, if I give you a particular example of what is called an atomic intervention, so we're going to take that variable x takes only one value, then we simply say that the factorization that we have is precisely what we had before. So the marginal probability of z, conditional probability of y given z, the conditional probability of w given x and y. And then because we're saying that x is going to take a single value, then there is no distribution in there. This is simply the Dirac distribution on value x equal small x. And again, in our example, in the previous example that we have looked at, suppose, for example, that we take the plant indoors. So we take the plant indoors, and maybe we're going to set some UV light on the plant, on top of the plant. So we're going to change the light that the plant is going to receive. And it's not going to be dependent on the location, on the latitude and longitude where the plant was before, but instead on the conditions that you're giving. And because it's indoor, then the water that it's receiving is going to be dependent on the water that you want to give to the plant. So it's not going to depend anymore on location. And then we get, again, a modified joint distribution of the data. But in this case, now the sun or the light that the plant is getting and the rain or the water that the plant is getting is not going to be conditioned on the location anymore, but is going to be conditioned on the conditions that you're giving, on the laboratory conditions that you're giving to the plant. And then where does this word of independence causal mechanism come? Well, it comes precisely from this fact. We're changing some of these mechanisms individually, and then the fact that we have changed the distribution of the rain or the distribution of the sun doesn't change how the function or the way in which the plant grows as a function of water and light. This is why they're called independent mechanisms. Okay, and then how does an intervention look like in do y, for example? So the first couple of lines are the same that we have seen so far. let's say that we don't know the functions, the conditional distributions that we have, so we can basically feed that from the data that we get as a data set. And then we can produce a new data set where we just simply intervene variable x to take value x equals 1. And then, as we see here below, the first column, which corresponds to the variable x, is going to be taking value 1 all the way. And the other variables are going to be taking distribution where variable x is going to be exactly 1. So the whole joint distribution is going to be modified, but the only one we're directly intervening in is on the mechanism of x. Okay, so now Eugene will talk about this in Causal.
Yeah, in the context of LLMs, based on our detailed introduction by Sahil on causality, I hope we are ready to go into applications. So how does LLM handle all of these causal reasoning? We're going to introduce a couple of work and with different detailedness levels. Let's start with a close look at how large language models can infer causation from correlation at this year's iClear. So suppose we have everything described in text carrying over the same spirit that was introduced before. Maybe we also could have a common sense data set or news articles mentioning as ice cream sales increase, the rate of shark attacks sharply increases. So what should our model infer? Should it buy this hypothesis that ice creams make you taste better? Or should it think that it's about getting warm, serving as a common cause behind more ice cream sales and more swimming in the sea, thus more shark attacks? So what it brings to us is that if we put all the variables mentioned in the text into the causal graph, then we will see a concrete application of this example. Correlation does not mean causation. So given a causal graph connecting all these variables, if we pick out two nodes, then very likely they are correlated. And the specific condition for them to be unconditionally correlated is that either one variable directly causes the other, vice versa, or they share a common ancestor in the node. I usually remember this type of things like how human genetics work. If two individuals have a lot of shared gene expressions, probably they have some shared ancestor in family history as well. So that's one way to explain correlation. And then the thing here is that causality, specifically in natural language, conveys the idea that either, let's say, C directly causes D, or A also causes D, but that just means a directed path without any reversal of the arrow direction. So as you can see, these two have different graphical properties. And then, can we go further apart from the negation result? It doesn't always mean causation. Taking one step further, either by intervention, can we, let's say, just intervene on the number of ice creams a person eats, and so on, or with causal discovery methods, with a lot of sort of credit attribution to causation prediction and search book by Peter Sperters et al. So one example of such is that if we are given a bunch of correlational statements as input, and we're asked to judge a causal relation as output, in this case, we frame the questions all to the large language models. And of course, based on the assumption that the variables are already extensively listed and it satisfies the faithfulness assumption and so on. So we can see that the negative example here basically corresponds to this correlation doesn't mean causation idea. Whereas this positive example mentions that A correlates with B, C correlates with B, meaning that each of them either causes B or has common ancestor with B. However, A is independent of C. So in this case, we know that A and C doesn't have common ancestor. Their relation probably is all built on this shared B as a result. So that's why in this case, we can infer that A causes B and delivering a yes answer. And with this spirit, our dataset basically extensively goes through all the possible causal graphs with 6 nodes, less than 6 nodes. And then the natural distribution of yes and no answers are around 20% yes, so 20% necessity cases. And we also publicize this core-to-cost dataset, which has a large number of samples to Hugging Face and GitHub. With this, we tested a bunch of language models from the random performance, which is corresponding to the label distribution of 20% F1. And then testing a bunch of open source models, we see Llama and Alpaca have marginal increase on the task, leading to 26 and 27. And also GPT-4 by the time of April 2023 was also only a little bit better than that. And by the time we closed up our experiments, we actually find that language models that are fine-tuned on natural language inference, a type of logical reasoning tasks, also tend to do well for this causal reasoning task. Bring this forward, of course, a lot of follow-up work continues this direction. Not only do the benchmark numbers increase, but we also see different variations of methods. For example, this first paper connects tool usage, so more symbolically grounded method to do causal discovery with large language models. Whereas the second paper, which has also been very famous across the community, focuses on keeping the trust in end-to-end text generation, but using axiomatic training to add different loss signals, augmented data to make LLM pick up causal reasoning still internally without relying on external tools. We think both directions are highly promising, and there will be more to see. Moreover, what are the applications? So some follow-up work looks at, let's say, how to parse healthcare conversations. Maybe they also have some correlation and causation nature. Some other things are when people respond to ChatGPT's responses, like how do they judge the correctness if there is such a causal or correlational confusion? And lastly, we also see a rising direction of LLMs being a data scientist, namely also performing quantitative reasoning given tabular data of these numerical values and so on. Lastly, I also questioned our team, why do future LLMs need this? So basically, the whole training corpus that LLMs are exposed to are basically full of these co-occurrences. Maybe in some contexts, ice cream sales co-occur with drowning cases and hot weather. In some other news reports, we see a lot of tech company CEOs are college dropouts. Is there a direct causal relation or something else? So when LLM goes through all these pre-training corpus or later fine-tuning corpus and so on, how should it process such information? Should it be correlation, causation, and what causes what? So that will induce a long-lasting research question in the domain. Moreover, we zoom out to see a full picture of LLMs for causal discovery. Actually, apart from the symbolic reasoning skills that we have mentioned, there are actually two types of skills. One is based on knowledge, namely, whether these LLMs already have enough knowledge about the causal graph or the mechanisms in its memory or after a retrieval augmented generation. And this reasoning skill, as we have touched upon, basically, to formalize it, it means we use we use the language of the ladder of causation in the Book of Why and many other Julia Poll's works. So basically, there is this ladder where it starts from correlation or association type of information, and then go to interventional causality, and finally, counterfactuals. So whenever we can use a lower run information, in the case of our tutorial, using correlational information to answer causal questions, it means that we're doing pure causal reasoning. Bring this forward, let's enhance our exposure to how LLMs use knowledge to handle a bunch of causal graph construction process. So this is one of the earlier studies, actually released in 2023 and now published at 2024 TMLR, by an amazing team of authors. They revisited a lot of traditional statistical causal reasoning questions and framed them to LLMs, such as this case, does changing the altitude cause a change in temperature or vice versa, where LLM actually have a pretty high accuracy without looking at the data. Moreover, scaling this up, not only for bivariate causal discovery, we can also see more follow-up works, and this is just one of them. There are many more on the GitHub list that we shared. They tend to focus on, let's say, causal graphs with more variables and go through pairwise queries of the existence of causal relations and build a graph connecting more variables. Moreover, although this is an intuitive way to handle causal discovery, we also meet with problems such as oftentimes LLMs produce more edges than the ground truth. For example, I think there's no blame that smoking might have an effect on pollution in that you did emit some bad air. However, it's probably a little bit trivial in the context of this ground truth graph where people want to understand the healthcare impact of smoking, pollution, on many things. So to solve this problem, we also see some follow-up studies, and this is again one example of such among many, that use LLM-guided discovery, which sort of combines the traditional methods on the left panel of the result table and like LLM-guided PC algorithm or LLM-guided camel method to reach a much better causal graph discovery performance. Here, the performance is by the difference between the ground truth causal graph and the discovered one. So the closer to zero, the better. This paper will also be presented on the COM workshop, so the Causality for Language Models workshop on Saturday. Lastly, in natural language, we also handle much more complicated causal queries. One example of such is this Tell Me Why dataset, originally published at ACL 2021. Basically, you can see questions that are contextualized in complicated stories, such as John was a student at university. He was attending a large class. The class was completely silent for a moment. He cracked his knuckles very loudly. So everyone turned their heads to look at him. Why did everyone turn their heads? Here, it's basically a little bit nebulous about the exact causal graph structure, but the actual reasoning is more grounded in story and how we can tell the mechanism immediately. And LLMs does give a pretty satisfying answer because the sound of the cracking his knuckles was very loud and sudden, and it broke the silence in the classroom. So bring this forward, we also have made a go-to survey for common sense causality with many of such questions that we have covered, but more on those reasoning that will depend on the knowledge base. However, just be aware that whenever we mentioned knowledge, it's a relative concept because there could be ambiguity in terms of what do you actually mean here. And also, the answers could be sensitive to cultural differences. I often give the example of wearing something white on your head, on your hair. In Chinese culture, actually means that there's something bad happened to your family, whereas in Western culture, it means pure and a lot of other cultural connotations. So the causal inference I could conduct when seeing someone wearing white in their hair should be very different across cultures. And then going back to these two skills, we further will get one more sort of introduction on the other type of pure reasoning, skill 2, as we have finished up the skill 1 introduction. So the remaining part, we will put it into the context of what we have introduced so far. So the causal discovery task, as represented in core to cause, basically cares about what variable affects which other variable, querying about the edges given the variables. There's also another type of causal reasoning, namely causal effect reasoning, which looks at the quantitative information of what's the strength of the influence of X on Y. And putting them to natural language examples, one can be lots of tech company CEOs are college dropouts. Does it mean dropout causes job success? And then the other one could be, how much does COVID vaccination increase the survival rate? And the second paper that we will dive into is this Clatter paper last year at NeurIPS, which show an description of how we turn causal effect reasoning to an LLM task. So assessing causal reasoning in large language models, we're actually motivated by this Israeli data, which was once used in some of my lab mate studies. So by 2022 August, actually from the statistics, people can see that vaccinated people in the region are actually more likely to develop severe cases of COVID. And then we raised the question, does it mean that the overall causal effect of vaccination is negative for health? Looking into the formal causal reasoning, we ground everything in the causal graph again. So the key question here is whether this arrow from vaccination to severity is positive or negative. And the thing to be aware is that there might be a hidden confounder of the vulnerability level of the patient. Basically, the originally more vulnerable group will have a higher vaccination rate and also higher severity rate once they got COVID. This inspires a common approach in causal inference that will adjust the vaccination effect for each vulnerability level. Just to put it into very layman words, you can imagine that we stratify vulnerability level to high, medium, low. And then for each level, there is this correlation of vaccination to severity. And then this method is called confounder adjustment, or in this case, it's backdoor adjustment as well. And with this spirit, we scale up our data set by taking prototypes from many famous causality books, such as Julia Pohl's Causality, Causal Inference in Statistics, Elements of Causal Inference by Jonas Dominic and Ben Hutt. So with these 10K questions, we formulate each query to LLM to be composed of 3 parts. The first one is the causal graph. Namely, we describe extensively which variable has a direct effect on which others, and then followed by statistics describing maybe across all the population, the vulnerable ones are how many percentage, and then among healthy and vaccinated people, the fertility rate is how much, and so on. Then we raise the causal query, does vaccination lead to an increase in the survival rate? Since we can automatically generate the statistics, we make the answers more balanced than the core to cause data. Namely, it's 50% yes and 50% no, depending on how much the causal effect is numerically. And ideally, as envisioned by many work previously, the ideal case would be how human causal scientists apply due calculus, one example of which is this confounder adjustment that we have just mentioned, or counterfactual reasoning we'll introduce later, but just keep it as a concept. So we use different statistical methods to get the causal effect. And then now we're contrasting the human ground truth solution with LLM-generated solution. Diving into the results, we see that from random baseline to some open source models all the way to GPT-3 Da Vinci are around 50%, so basically knowing not too much about the causal effects. And then the models with more instruction tuning gets stronger causal reasoning skills. And GPT-4, by the time we publish our paper, also has a clear margin over the previous ones. And then we raised the question of how much more performance boost can we expect? So we proposed this causal chain of thought prompting, causal COT, which takes in this exact question and develop a 5-step process addressing the problem. From parsing the causal graph, ground everything formally, formalizing the query, such as in this case, it's an average treatment effect from vaccination X to the survival rate. And then we use the do notation to denote intervention on vaccination or not. Then it's statistic collection, trying to get the numbers from the given information, followed by formal causal inference steps, as mentioned, such as confounder adjustments, and evaluating the mathematical expression in the end before deriving at the final answer. So bring this to the clatter performance, we see an 8-point improvement. And a rough test for a grad student at that time reached around 80% accuracy. So it's really like one step forward. We welcome people to test the questions again on O1 and also some newer other LLM models. And you're also very welcome to regenerate the clatter dataset because we randomly sample a lot of numbers. And you can also change the yes-no questions to the actual numerical answer, just as how GSM-8K evaluates its performance. And to conclude this work, I think the insights for future work is that we really look forward to, like as mentioned, some basic mathematics are also shared in some other data sets. So we really look into the uniqueness of clatter or causal reasoning as a data set. I think, at least in the context of clatter, the really challenging part is query formalization. Maybe this question, does vaccination lead to an increase in the survival rate, is pretty clear. But then if people ask, is there a gender bias in the price selection or admission process, then different people might care about different definitions of gender bias, which poses challenge on the formalization step. The other case is to execute the formal causal inference steps really accurately. Some takeaways for clatter, or all the way until here, is that we treat the problem as how a human scientist would do, understand it and ground it formally, design a set of structured steps, and use LLMs, like we potentially suggest a future work to also use LLMs to connect with tool use and deliver scientifically grounded results. Moreover, using the last 10 minutes of this session, part 1 on causal reasoning, we want to show a bigger picture of causal questions for future chatbots. As mentioned, we propose to add to the existing skill sets from direct generation, RAG, simple math, and data science to extend to causality as a reasoning skill. And moreover, the question that Core to Cause, Clatter, or previous work covered is a tip of the iceberg of all the questions that humans care about. If we look at the causal questions that humans can ask, of course there are lots of questions, such as attributing the reason of an application rejection to lack of experience, so a bivariable causal discovery. The other question could be, should I get a PhD? Which many of us must have asked ourselves before. Here, what is clear is that the cause is getting a PhD or not. What is unclear is what does the user actually care about? And then it requires LLMs to infer, do they care about income, happiness level, and many other things. So it will be inference of the effect, then causal effect reasoning. Moreover, we admire great scientists who question, why do apples fall? Or all these mechanism questions. And apart from physics, we also care about how to make our society a better place, where also in the process of doing this project, we realized that every how-to question basically presents an ideal effect and queries about all the causes and ways to lead to that, which is pretty aspiring. And moreover, I think everybody consciously or unconsciously care about what are today's actions influencing what will happen tomorrow. Well, of course, we cannot solve all of these questions. So we actually present a question investigation one and opening the space for all the people who are listening to this tutorial to take these questions and see which one can we conquer and which one should we work towards. So we have this 2024 paper on analyzing human question behavior and causal curiosity through natural queries, where we cover a broader taxonomy of causal questions driven by the examples that we have went through. For example, not only do we care about edges, we also care about what variables does there exist. Not only do we care about by how much does X affect Z, we also care about, can you give me the exact function and mechanism? So these are questions about the variables, the edges, the causal effect, and the mechanism. And if we specify everything clearly, then the change in my income after a PhD type of question is a type 3 causal effect question. Does smoking interfere with drug effect is a causal edge question. If we look into the history of science, for a long time, people were curious whether phlogiston exists as a component to start a fire. So to understand the key elements that are really needed to start a fire, it's a question of type 1. Lastly, since I've read a lot of chemistry before doing the tutorial, so every chemical reaction basically is a mechanism question because you know the mass of these elements and you know the equation, then you can induce a lot of other things. So to capture human natural curiosity, we include questions that people ask in different channels, from search engines, community forums like Quora, and the shared GPT or wild chat interactions that people share online. And then they cover a relatively wide set of natural emergence of curiosity. So we get subsample it because it's way too massive. We get 13.5K questions, where we found that 42% of these natural questions are causal, namely fitting in any of the 4 types that we have mentioned by a combination of LLM and human-in-the-loop classification. Moreover, we can have a glimpse over what are in these questions. As I've illustrated before, how and why questions are often causal, and then what, who, where questions are usually more non-causal. Moreover, we also look into the level of cognitive skills needed for causal questions, taking this Bloom's taxonomy, starting from the easier skill, memorization, to understand, apply, and so on. We see that among the non-causal questions, a majority of them are about remembering, so more than half of them. However, for causal questions, they're heavily about applying, evaluating, understanding, and others. And to solve them, we didn't present a solution and await future work to make progress on that. We evaluated roughly how GPT-4o by the time of this work perform on it, on the axis of how effective the answer is, how efficient is the generation, is the conciseness of the answer, and how satisfied are the user. And we discovered that LLMs usually struggle when asked to foresee the causal effects in the future, something that hasn't happened. It does well in answering causal questions that require knowledge lookup a lot, like smoking causes cancer and so on. Lastly, the answers are usually overly verbose, namely a very low efficiency. As many of us might have the user experience, it tend to list all the possible considerations and generate a pretty long answer. And then bring this forward, we also think about among all these questions, as we already mentioned, there are 4 different types. Then maybe not all of them should be routed to formal causal inference, and maybe a lot of them could be solved by this mode 1 direct generation or mode 2 RAG paired with web search and so on. So we further did a classification, human annotation, and realized that actually the result is pretty optimistic, around 50-50. So 53% of the questions can potentially be addressed by formal causal inference, leading to the future of more reliable LLM answers to causal questions. As takeaways for this part 1, the space of natural causal questions shows the great potential of causality to chatbot AI. Future work is needed to address these causal questions in a more scientific way. Lastly, it's also promising to compare the effectiveness of skill 1, namely knowledge-based causal reasoning, and skill 2, formal causal reasoning, on these questions and see which one should be the way forward, or whether we should have a router to pre-process questions and give it to the right way of solving them. With this, we will proceed to the second part, which is connected, but changing the research topic from querying about causal effects in the world to interpreting LLMs by causal methods. So, as we have seen, the subject of causal inference has changed throughout history. A lot of the questions used to be about how nature works, which covers the modern subjects such as physics, chemistry, biology. From the last few centuries, we see a surge of interest on how human works, from body to mind. And that covers advancements in healthcare, neuroscience, psychology, sociology, and many others. Lastly, from recent years, we have got rising interest in how do these LLMs work? Can we interpret their causal mechanisms? As a big shift, we see also an urgent need to understand how it works. Inspired by some of the Zurich AI gathering, people recommend me this blog post on MIT Tech Review. Nobody knows how AI works nowadays. And moreover, even if we don't know how it works, people ask it really high-stake questions, maybe about their own health. I have a strong chest pain. Should I see a doctor? And then in this example, the LM responded, don't worry, this can happen. It's recommended to first wait a day to see if the pain subsides on its own. It could be correct or it could be incorrect and causing a big harm on the user. So for that, the goals for LLM interpretability is really a responsible AI question. We are curious about the following questions, just to formalize these 2 keywords, LLM interpretability, to actual research questions. The first question, why does LLM succeed? The second question, why does it fail in some cases? Third question, what is its basic unit of representation and mechanisms? To extend it further, one example of why LLMs succeed could be interpreting how LLMs do math, as we see a lot of popular research in social media and publication spaces on the vast progress of mathematical reasoning for LLMs. One example for why does it fail can be interpreting the gender bias. Why does it show different probabilities for male and female and others? Then this leads to a further question, how to improve it after we see success and failure. One example could be a paper that I really liked at SAML 2024 on how to actually remove toxicity after interpreting it. Lastly, what is the basic unit of representation and the mechanisms in LLMs? Where we will cover some interesting work on sparse autoencoder and others. So before diving into details and also connections to causality, we will first have a broad overview of the landscape of methodology to understand LLMs. So I usually compare things to related subjects. One example is how we test our own students. The other example is, as computer scientists, how do we do software testing? Let's say that analogously, if we receive a program and it's an executable file on our laptop, different from how we design exams to test human students, there are also behavioral tests to check whether the software is performing right, like different unit tests or different input-output things. And the second thing is about intrinsic tests. Namely, because we have this software, we have all the low-level codes of it, we could inspect its internal execution process. And turning this into LLMs, we also have this deterministic function if we set it to greedy generation. And then LLM is no different, just abstracting it out. It's no different from y equals fx, just that this f has a lot of parameters, hundreds of billions and even more. So the general paradigm of how we handle it, usually, let's say if we're familiar with some LLM usage, then it's like, okay, we have a black box, then there's some input text, we expect some output text, and we want to make sense of what's happening here. There are two ways of making sense of it, as we have just mentioned. And for the behavioral test side, we have a causal variant of it, namely, in the input side, we can vary the many factors that's able to be changed and intervene on them to see LLM's reaction to each of the single factors. So getting more detailed introduction to how behavioral tests work. If we start from some common way of how researchers talk about LLM performance before we form an understanding. We might see things in the format of a performance table. Maybe when GPT-4 was just released, then it performs this number on uniform bar exam, that number on LSAT, and so on. And then, so not only the absolute number, we also report the relative percentile among human testers. Moreover, to dive into a deeper understanding of what's happening, we really recommend a causal framework to understand the structure of the input. So taking again this very popular example of math reasoning, some standard questions could be in the format of, John has 10 apples. If he gets 10 more apples, how many will he have in total? Where the ground truth answer is 20. Putting everything into the causal graph, we can see that both of the numbers 10 and 10 are operands. The rest of the text is the text template, and the template can be split into text that's relevant to the math operation O, namely more apples instead of less apples, gets instead of loses. There are also text surface form that's irrelevant to the math performance, such as whether it's John or Jack, or whether we change it to a female character, and is it apples or bananas, and so on. So, and then the other variable is the model prediction, 20 here. Connect everything into a causal graph. There's probably a confounder behind how humans usually generate test templates and the operands. And also, there exist some middle variables, such as the correct way of solving it must have the correct arithmetic represent somewhere in the internal state before leading to the model prediction. And then when we talk about robustness or probable failure modes of the models, One example of such is if there exists any other edges that doesn't go through the correct arithmetics. Let's say some word biases, maybe LLMs does really well on common names, but fail when the names become more infrequent. And also there might be that number bias, like 10 and 10 are really frequent numbers, but once it's changed to other ones, then it will have a failure mode. And the causal framework for behavioral tests basically means that we can intervene on many of these variables individually. We can intervene on the operands and see the total causal effect just from the numbers, regardless of all the other things. We can also intervene, like control for the answer to be the same, but change 10 and 10 to maybe 2 and 18, 3 and 17, to see if there's a number bias, apart from the correct arithmetics. Bring this forward, as many of us might have seen, recently there is this work on GSM-8K symbolic, GSM symbolic, where they also take a structured way, let's say take the GSM-8K mass reasoning data set, but then have a lot more causal variables. Some of them could be the name, whether the name should be Sophie, and then whether the relation should be a nephew, and all these numbers and so on. Then on the right, there's a structured way of how everything should have been connected to each other by the correct mechanism. And then after the structural change, like sort of systematically changing many of them using the symbolic template, then the results that they show is basically a total causal effect. So this graph, the x-axis is different models from Mistral, Gamma, all the way to GPT-4o. Whereas the y-axis is about changing the original data set to the perturbed template. How much accuracy drop does there exist? So basically, this quantity is a total causal effect of changing all the factors and mixture of such. Which is a common way of doing this behavioral test for LLMs. However, since we will dive more detail to intrinsic tests, we need to motivate what are some potential limitations of keep doing this, although it sounds really plausible and then we can try a lot of things. Mainly, we started with the question, why does the LLM succeed? However, with behavioral tests, we can, for a lot of cases, understand, does it succeed, as always? Namely these benchmark numbers. Instead of why does it fail, we actually answer the question, does it fail, by trying all the input perturbations. And for how to improve it, there could be some methods, such as using this generation to do data augmentation, and further maybe constrain the model to be aware of certain things for future training or fine-tuning. And lastly, for the more important scientific question, what is its basic unit of representation and mechanisms? We basically don't have an answer. With this, we want to highly motivate a very promising thread of research on intrinsic tests for LLMs. So to motivate a little bit before I give it to Sahil, so for every intrinsic test, as we mentioned, originally a lot of models are black box ones where we just had the input-output correspondence. However, if we try to open it to MLP layers, attention layers, all these transformer blocks, we might get interesting results. And also, just to motivate, a lot of us, when talking about interpretability, actually thought about, we're going to talk about sparse autoencoder, SAE. So just to fully describe what it means, basically, sparse autoencoder is a way, so that it's a variant of autoencoder, which is previously heavily used in machine learning. So given an input using, in this case, like a 1 MLP layer to a higher dimensional hidden layer in the middle before reconstructing back to the output. And there are two types of losses. One is this reconstruction loss between the input vector and output vector. The other one is regularization over this hidden layer so that it can be as sparse as possible. As we can see, a lot of the nodes are white and not activated, so that if we focus on the actual activated ones, we can get a more clear interpretation. And also, the interesting things to SAEs are actually this decoder matrix, where it translates how, so basically the activation is about what information does the input provide, whereas the decoder weights that have been learned, also called like dictionary learning, has a lot of features that can be interpreted in interesting ways. And in the context of LLMs, basically people change this general input vector to LLM's internal representations. Using that, basically it means that if we have a bunch of transformer blocks, usually in some of the medium layers, people learn this sparse autoencoder and take what are this decoder matrix or dictionary that has been learned. Some examples are that maybe some of the features correspond to every word that's end with ing. Some other features could be chemistry terms and so on. And if we look at one of the blog posts by Anthropic this year on scaling monosemanticity, when they learn a really large set of features, like extract millions of features from the trained large language models, then one example is one of such features is actually correspond to Golden Gate Bridge. And the interesting thing is that so they try to feed a different type of text input into it. And then these text inputs that are highly related to the introduction or mentions of Golden Gate Bridge usually activates such feature very strongly. Moreover, such behavior was also observed across languages and also across modality from images and so on. And then there are also some interesting results in the exploration space where they clamp that feature that has been learned to 10 times its maximum activation value. This actually induces thematically related model behavior. Namely, when we originally asked the model, what's your physical form? It answered, I don't actually have a physical form, I'm an artificial intelligence and so on. But then once people exacerbate this feature, LLMs actually self-identify as, I'm the Golden Gate Bridge, a famous suspension bridge that spans across the San Francisco Bay. So these are really interesting results and remind me, and I'm sure maybe many of the listeners here, of an earlier example for NLP models on sentiment neuron. So there was this 2017 paper where they didn't do such complicated things such as the SAE, but they directly tried to interpret what's inside the neurons. So they trained the NLP models to predict next character in Amazon reviews. And some correlational claim they made is that there exists a single sentiment neuron that's highly predictive of the sentiment value. And the causal claim they have is that if they override this sentiment neuron, it can generate sentences of an opposite sentiment, such as changing nice fitted pants and so on, a very positive one, to the package received as blank and has no barcode, a waste of time and money. And also they plot the distribution of sentiments across high values of this neuron and low values of this neuron.
So now let's talk about causality in the context of interpretability. And the main idea whenever we think about interpretability, causality in the context of interpretability is that these very large language models, they constitute a graph by virtue of having some input and output and doing some intermediate operations. They look very similar to the causal graphs we saw in earlier parts of the presentation. So the idea in here is that we will start hopefully defining some variables that are going to maybe be some intermediate variables, some parts of a model that we can modify, let's say, through interventions. And in addition, we can also modify the text in the way that Eugene has explained so far. And maybe that in addition to some other tools of causality would help us a little bit open this black box of how do these large language models work. So then some of the typical questions that we think about when we're thinking about interpretability is whether certain parts of a model are responsible for certain type of behaviors. And then this is very classic example would be maybe gender bias or toxicity. And maybe we can think a bit of the alternative question, which is, okay, if we have already a behavior, if we have defined a behavior, can we find the parts of a model that produce that behavior? And then, as I was mentioning just before, we can use some tools from Causality, just like intervention or causal mediation analysis, and a little bit later, causal abstraction and representation learning, basically to solve this type of tasks. These are all causal questions. Okay, so let's use a motivating example here from a paper from 2020. This is from JCV and co-authors. So let's think about the following example. We want to figure out what part of a model is responsible for gender bias. And the way we're going to do this is we're going to first look at a particular prompt, that is, the nurse said that. And then let's say the stereotypical candidate would be that the next word would be predicted she with high probability, and the anti-stereotypical candidate would be the word he. How do we think about it as whether a model is biased or not? We simply take the ratio between the probability of responding she over the probability of responding he, or stereotypical over the probability of anti-stereotypical. And if they're close to 1, the model is not going to be biased. That's kind of the outcome variable we're thinking here. And their hypothesis is that we could localize, if a model is biased, we could localize where does the bias happen? Where does the model act in such a way that that this ratio between the stereotypical and anti-stereotypical answer will not be 1. And in the language of causal inference, these are called basically mediators. Again, assuming that the language model is a causal graph. Okay, so now let's talk a little bit of mediation analysis. So very simple causal graphing here. This is very similar to what we have seen so far, but I'm just putting causal names in there. We have a treatment variable, which is going to be the input text. We have a mediator, which is going to be maybe some part of a model, and we're going to have certain effect or target variable, which is going to be this ratio between the probabilities of the stereotypical and anti-stereotypical variable. This is, again, what we were just explaining before. The nurse said that, then maybe the mediator can be a neuron, an attention head, maybe some group of neurons, and the moral prediction would be some ratio of probabilities. And then maybe we can think of the treatment, of the intervention on the treatment, to change the word nurse, to change something to where we clearly know the answer, for example, as the man said that, and we would expect that most generally in that case, it has to give the anti-stereotypical answer, which is he. Okay, and then the thing is that whenever we're thinking of causal graphs like these, we can do interventions in different areas of a model. And this is where causality is going to help us, right? Because we can do an intervention on the treatment, as Eugene basically has said before. We can do an intervention on the mediator, or we can do interventions on both of them. And then where do we intervene, or what type of quantity do we want to look after intervention, so that this is going to tell us what we want to know? That's the big question in here, and I think causality is a very good toolbox to answer this question. So let's start with the total effects. The total effects are basically simply taking the effect of a change in the treatment variable as a whole through all of the possible paths that we're looking there. So a little bit in the language that we have seen before. So we have this control group, which is the prompt, the nurse said that, an intervention, which is the man said that, and basically the total causal effect is going to be the expected value of our outcome variable, the ratio between two variables, whenever we use the nurse said and the man said. And then this is only taking into account, again, all the paths at the same time. But then, as maybe you realize, this is not going to allow us to figure out which are the units within the model that are potentially producing some form of bias. So maybe we want to do better, and we want to know some intermediate paths. So to see how the total effects would work, using some figures from the amazing paper, we just simply propagate forward using the word nurse in the prompt that we were talking about. We propagate using the word man, and then we simply compare the expected value of the outcomes in both cases. And then again, we maybe need we need some effects through the mediator itself, and we need some effects through the mediator, because in that case, we're going to be able to tell, okay, maybe this neuron, this attention here is the one that produces the bias. Okay, so before I continue, I'll just ask everyone to hold very tightly to your chairs, because we're going to do a tour de force through structural causal model and counterfactuals. If you're standing next to the wall or sitting next to the wall, grab yourself to the wall. Okay, so what is a counterfactual, semantically speaking? Okay, let's say first I have the sentence of what would it be in, let's say, philosophy terms, and afterwards I have an example, and I have highlighted some words which are corresponding between the two of them. So counterfactual, semantically. Given the current state of a world, what would happen to an outcome of interest, a target variable, if certain elements of the state of a world had been different? And the example, and I'm going to maybe draw some parallels in there. So let's say, given the current economic and societal state of the world, industrial revolution, technological revolution, what would be the current CO2 emissions had LLMs not been introduced a couple of years ago? So we have this element of the current state of the world. The industrial revolution actually happened, the technological revolution actually happened. We modified something little in there, which is what would happen if LLMs had not existed, and then we look at a particular outcome of interest, which in this case are going to be the world emissions, CO2, something like this. And to understand these mathematically, we first need to understand what structural causal models are. And structural causal models are going to be very similar to the graphs we have seen before, but there are small details that we just have to differentiate. So structural causal model is a collection of structural assignments. For each one of the variables on our system, we're going to have one function that is going to depend on the causes of that particular variable, and it's also going to depend on some independent noise. And this function of the parents of the variable and the noise itself is going to be a deterministic function. Notice that whenever we assume that we have some independent noise, this is an assumption. This is not something that is given to us by the definition itself, but we're assuming that. And then this is equivalent to having what we call in causality sufficiency. And basically what this tells us is that we are observing all relevant variables for the system that we need. Okay, and then maybe a very important detail in here is that even though the functions that I mentioned are deterministic functions, they induce a conditional distribution on the variables by virtue of taking independent noise as function of it. And then because there is going to be this probability distribution, there are going to be conditional probability distributions, they also induce a causal graph in the sense that we have observed before. So basically what I'm telling you is that these structural causal models are slightly more general than the causal graph itself, because the causal graph is basically something that we can derive from the structural causal model itself. Okay, again, so let's look a little bit of this pseudo-coding here. The idea is that on the left, we have what the way that we defined a causal graph before. So basically, all the dependencies of the parent variables are within the distribution. And on the right-hand side, we have structural causal models where the noise has been basically abstracted from the function itself. And even though these two essentially produce the same observational distribution, if we had a data set containing, basically generated from these two data processing here, there is this difference between one being the result of a deterministic function where the noise is taken as input of the function, and the other one where we are sampling directly from the conditional distribution itself. Okay, and then now that we have this idea of structural causal models, we can also come back to understand what an intervention is. An intervention is very similar to what we had seen before. We can modify either this deterministic function itself, we can modify the dependence on the causes of xi, or we can modify maybe the noise that is part of the structural causal model itself. This will again entail an intervention or a change in the mechanism in the conditional causal, and this will also produce a change in the joint distribution of all of the variables at the same time. Okay, with this, now let's look at the counterfactuals. And yes, this is going to be a little bit tough for a second, but I hope that I have your attention now. So current state of the world is basically an observation, right? So we have observed all of our variables until now. This is basically the red box on the left. We assume we have a set of functions, and we're going to have certain technical assumptions about invertibility. They don't matter that much now, but we assume that using these observations, we can find what would be the noise for each one of these variables, for each one of the variables of interest. This in counterfactual language from Pearl's book, or Pearl's theory of causality. This is called the abduction step. With the observation, we get let's say, the noise. Now we have the action step, which is, we know the structural causal model, we're going to act on the system, we're going to change something on the system, and this is what I mentioned before about the state of the world being different. So in our case, in the example that we had before, we're saying LLMs are not introduced. So let's say variable xi is, LLMs were introduced is 1, if they were introduced, and then we're going to change that to be 0. And then this defines a new structural causal model because we have changed one particular mechanism. And in order to do prediction or to understand the target variable of interest, we simply propagate again through all the structural causal model, now modified one, all the noises that we had, and then this is going to give us all the new values of the variables that we're interested in. This the step of prediction in counterfactuals. Abduction, action, prediction. Okay, congratulations, we've made it through the counterfactual part. Maybe it's important to say that the noise that we're using is the one that we found before through the observation, but we already know that. And then the last important thing to say is that all of these that I have explained so far, we have only spoken about an individual, a single unit. So the thing is that counterfactuals, they're at the unit level and not at the population level. When I spoke about the state of the world, I was talking about this world in which there was an industrial revolution, this world in which there was an technological revolution, but there are many alternative worlds we could look at that have different, let's say, states. So we're looking at only one unit whenever we're looking at counterfactuals. Okay, with this, we can go back to the mediation analysis and remember that our main goal is to understand interventions or causal effects through some of the paths of the causal graph. So let's look at a specific path-specific causal effect, which would be the natural direct effect. And I'm showing here more or less the goal of it. So we want to have the natural direct effect is simply going to be the red arrow that we observe on the causal graph. So we want to observe what is simply the direct effect of intervening our treatment on the effect. And to do this, we need to do two propagations of the LLM if we're going to think on those terms. In the first case, we're going to propagate the control group, so the nurse said that. On top of that, we're going to fix some of the mediators, some of these neurons or attention heads that we chose before. We're going to fix those values. We're going to fix those values. And then we're going to propagate again the LLM, now this time with the man said that, but instead of propagating it through the whole network as like the network as in its initial state, we're going to leave those fixed elements by the first propagation. How does that look like in using the figures? So as I mentioned, we propagate first with the nurse set, we find the value of z while it's frozen, and we propagate again using the word man instead, but in this case, we have frozen the values of z. Okay, and then there is a different effect that we can look at, and that's going to be the natural indirect effect, and that's going to be the effect through the mediator as well. And in this case, we need to do 3 propagations instead. Okay, first propagation is going to be the variable in control group. So the nurse said that. And then that's going to give us what we're subtracting from this indirect effect. Second propagation, we're going to do inference on if the treatment being 1. So we're going to say the man said that. We're going to find the mediator value in there, fix that mediator value, and then the third propagation that we're going to do is simply propagating again the basics, the control group, which is the nurse said that, but in this case, just in the case before, the mediator is going to be fixed, but now to the value if the treatment had been changed. And again, we can look at the figures. They are quite telling, let's say. These are the 3 propagations. You can maybe see what I was talking about before. Okay, so Jijing is going to tell us about some of the applications of this for.
Yes, just adding a couple of slides here. Based on the introduction we have, there are actually also a lot of different applications. As mentioned, apart from gender bias, there are also network structures that capture toxicity in the expression. For example, from this Lee et al. ICML 2024 oral work, they found that within the MLP layers, actually top tokens of different types of toxicity could be located in certain vectors. And moreover, if you do a deeper read into the work, they actually did a 3-step process from first mechanistically understand how toxicity is generated, then reduce it actually with DPO training, and finally mechanistically understand why it was no longer generated after DPO. Moreover, apart from interpreting each single mechanisms and locating these, we also have work on how the interplay of multiple mechanisms when they might need to contradict each other might look like, which is called competition of mechanisms. And then we will go back to more fundamental questions.
So we all know that these models have billions of parameters. And then something that I kept secret or that I swept under the rug was which one of these, maybe neurons over attention heads or group of neurons, do we choose as the mediator variables that we need to freeze, right? And probably you were all asking that question and you were annoyed that I hadn't answered that question. But the truth is that these in the some of the earlier works, these were done by the research who were doing. They said, this looks good. Maybe we should try this attention head. Maybe we should try these neurons, and that maybe we could improve on that by using some causal methods. And the question is, okay, can we find a way of automatically deciding which of the units are the important ones here? And then maybe even a little bit more subtle question is whether this automatic decision is well defined, because we can always take increasingly number of neurons from the model itself, and then let's say if we leave only one little path of the large language model, well, certainly everything, all of the model, but one little path is going to capture every behavior or almost every behavior we're interested in. So these are some important causal questions that we might want to look at. And to try to answer the first question, because the question of well-definedness is a bit more difficult, we're going to look at causal abstraction and causal representation. This is also very recent research in causality. And then basically the idea is that so far, again, we have assumed which causal variables we know. Maybe you recall from the first part of the presentation, I mentioned we have this assumption that we know which columns of our data set correspond to variables themselves. And then I said maybe pixels, if we had pixels, we cannot know which are the variables. So the idea is that in many cases, in many types of data sets, we can't say which are the variables of interest, but we need to make a choice of that. And causal abstraction and representation helps us to do this. And essentially, the idea is that maybe we have some low-level measurements, and then maybe this is very high dimensional. In my case, I have 9 variables. This is not so high dimensional, but it can be very high dimensional. And we want to aggregate some of these variables into a larger model, into high-level causal variables, and then this is going to make it easier for us to, let's say, interpret the models or do other type of tasks. And then, what are some of the differences between causal abstraction and representation? So in causal abstraction, there is no assumption of the uniqueness of the family of high-level variables. So basically, some of the questions that we're asking is, okay, can we find maybe some form of aggregation function that is going to be causally consistent in a certain way? Or maybe we have a low-level model and a high-level model, and then we ask the question, what is the function that maps from low-level model to high-level model and then keeps this causal consistency? Whereas in representation, researchers assume, let's say, that there is a true data generating process, a true high-level model, and the questions that they ask is, okay, under which conditions can we identify this unique model? Under which conditions can we learn it as well, the aggregating function? Okay, and then I'm going to give one particular example of abstraction and representation in language models. So this is a paper by Atticus Geiger and some of his co-authors, where they had introduced already distributed alignment search, but this is an example use of this. And the idea is that they assume that they have a neural model, so they have the LLM or some model that implements some behavior. And then they have a causal model that represents causally that behavior itself. So they need to assume that there is a high-level causal model. And what they do is that they find some form of alignment function, this function that maps from low-level models, so from this neural model, to the causal model itself. And then the way they do is, so there are a lot of technical details, but then basically they find a rotation matrix that rotate the variables, the hidden layers of this neural network. They make these into, let's say, potential high-level causal variables. And through this idea of interventions, they check, okay, suppose that I change this rotated variable, and I intervene on this rotated variable, and I intervene on something that I assume, maybe hypothesize in the causal level, on the causal graph, that it would be changed. Does that produce also the changes downstream that I would expect from the causal model? And then they use interventions as the inductive bias to learn this alignment function from low-level model to high-level model. So this is one of the, let's say, first attempts at using causal representation and abstraction to do some interpretability of neural models. But notice that here we're assuming that we have the high-level causal model, and maybe this is very strong because this also assumes that we will need to have the high-level causal model of any other behavior that we are interested in, and as we have seen so far, this is a very big thing to ask. So then I'm going to give just two couple of ideas that might be interesting for people to look at, and that is, for example, if we can maybe define some target variable. There is some work on causal abstraction that allows us to do abstraction of the variables as long as we know this target variable. So maybe maybe if we can find this notion of target variable, maybe that could be a potential way of finding an abstraction. But moreover, maybe we can also use some current methods in interpretability, like those that Gigi already mentioned, like sparse autoencoders, as a pre-processing step before doing causal abstraction on those variables. So maybe something like a post hoc analysis of these features that we find. And with this, I think I'm going to give it to you.
So as a summary, I know already everyone is excited for our upcoming panel. So just a quick summary and a recap of what we have went through in this 1 hour and 45 minutes. So in the first hour, we covered causal reasoning LLMs. I hope you can still remember what is causality, what are the graphs, and all the conditional probabilities. How do LLMs perform causal reasoning now? Like the two different tasks, causal discovery, effect reasoning, and what are the future research directions that can further enhance LLM causal reasoning? This knowledge versus pure reasoning approaches. And in the second hour, we have covered causal methods for LLM interpretability, where we look into how we can understand its decision-making mechanisms from the behavioral test to intrinsic test, and what role does causality play? How do we use these interpretations to improve future models would be an open direction. And moreover, I welcome everyone to stay tuned for other events on causality and LLMs at NeurIPS. There are a lot of papers, so definitely the poster sessions and talks are interesting. Moreover, the December 14th Saturday, some of our lab mates and many others organized the Causality and Large Models CALM workshop. And on December 15th, Sunday, we have the workshop on causal representation learning, where co-organized among many other very nice people. And lastly, just a quick overview. We covered causal reasoning LLMs, we covered interpretability, and for the panel, we will use it to understand what's the future of causal LLMs. Namely, do we need causality for future LLMs? If so, in what type of role? So we will take a little bit of time to set up the panel. Hello, everyone. Welcome to our exciting panel on what role will causality play in the future of LLMs. I guess we will start from, I don't know, maybe in-person, online, in-person, online, in-person. And the first question is maybe tell 1 to 2 sentences about yourself and how you get into causality and or LMs. Starting with Joshua.
Thank you. How did I get into all this? Actually, when we started thinking about deep learning of representations in the 2000s, my thought was, well, what would be the ideal representation? It would be the causal factors explaining the data. This was a time when we were doing unsupervised learning with things like autoencoders and Boltzmann machines and things like that. So generative models. But really, what got me to better understand these things is Bernard, who's been thinking deeply about this much before me, and of course many others before, like Julia Pearl. And in the last, let's say, 6 years, I've been doing more technical work on the causal side. Of course, my connection to large language models is even longer. In NeurIPS 2000, we had a paper called Neural Language Models. That was maybe the first doing this sort of thing. Very small in comparison to today's.
Awesome. Thank you so much, Joshua, for the intro. As he already hinted, we will give the mic to Bernhard. Hello.
Hello, yes. So I think my first time I learned about this was during a conference which was called the Interface. I think it was a conference organized by statisticians, and I had to give a talk about kernel methods, and Julia Pearl was giving a talk about causality, and I found it absolutely fascinating. But at the time, it didn't change anything in my research trajectory. I was very much into kernels and everything one can do with kernels. And then maybe, I don't know, 10 years later or so, I got interested again, and that came through a student who asked Dominic Janzig and myself if we can advise a master's thesis and later a PhD in causality. And I think I'm very much interested in causality from a mechanisms of physicists' point of view. So I think the world, the dependencies in the world are due to mechanisms that generate data. And the task in causally inference or in causally influenced machine learning is to discover these mechanisms and use them to learn robust things about the world that may generalize across different distributions that are robust also with respect to interventions, etc. And I think many of the open problems of machine learning are related to that.
Awesome. Thank you so much, Bernhard. And we'll pass on to GB.
Hi, everyone. I'm Giambattista, or GB for short. My connection to causality, I did my PhD with Bernhard, and actually also Joshua was on my PhD committee at the very end. But then since then, I moved on to mostly doing LLMs research at OpenAI. And I'm a research lead and one of the foundational researchers of O1. And yeah, I'm mostly interested in LLMs and reasoning these days.
Exciting. Now we'll do an OpenAI DeepMind swap, and we'll connect the online DeepMind London first before moving to Mountain View Gemini team. Yeah. Tom, welcome.
Thank you. Yeah, I'm Tom Everett. I'm a researcher at Google DeepMind. I'm part of the AGI safety and alignment team here. So we're working on how we can anticipate and mitigate risks from powerful future AI systems. And I lead a sub-team that explores causal approaches to this, as well as the external causal incentives group. So I come to causality from an AGI safety background. In my PhD thesis, I worked to formalize various AI safety problems and solutions, and I realized that what was doing the work in most of the proofs and arguments was the presence or absence of some causal relationship. So that was really my way into causality. So over the past few years, we've been working on incorporating more and more perspectives, more and more AGI safety questions from this causal perspective. For example, how to understand an agent's incentives, you really need to understand the causal relationships of the environment that the agent is embedded in.
Very cool. Yeah, exciting to have your diverse background of knowledge here to make the panel more interesting. And lastly, we will welcome Swaroop.
Hi, I'm Swaroop Misra. I'm a research scientist at Google DeepMind in Mountain View. Work in the reasoning for Gemini. I've been background in instruction following, reasoning, more recently in superhuman reasoning, like IMO and this kind of stuff. Excited to recently started to explore causality and excited to see how can we build more and more powerful LLMs inspired of some of this research in causality.
Very cool. Awesome. Then, given this and given the audience, like the panelists' background, I actually want to start with a definition question first. So it's a little bit continuation of what is causality, and it's in the context of Swaroop is the co-organizer of the Math AI workshop that will happen soon as well. And in our tutorial, we heavily covered GSM-8K, GSM symbolic, as well as the recent O1 release. I see a lot of demo things are on how it addresses math questions. So I wonder how all the panelists, maybe in a similar order, or how you think about the differences between causality and math reasoning.
I think that in math, you can go from A, implies B, or B implies A, and both orders might be okay. Whereas in reasoning, we have this asymmetry. And usually it might be revealed through time index, for example, or, through the experiments we can do with intervention, which wouldn't be exactly applicable in the math case in general.
Yeah, totally. Ferhad, how's your thoughts?
So I would like to argue that both the formal framework of causality, in as far as it exists, and also the formal framework of mathematics are abstractions of things going on in the real world. So as a physicist, I like to think of mathematics as an abstraction of things that come from physics, And maybe there it's clear, but in the case of causal inference, or maybe even in the case of logics, predicates, logic, etc. I remember once I took a course in history of philosophy, and in this course we learned that there's actually reason to argue that even syllogisms, so classical patterns of logical reasoning, are abstractions of human reasoning. So people noticed that certain patterns of argumentation in discussions were more convincing than others. And then people formalize these patterns and say, this is the modus ponens or the modus tollens, etc. So the formalization comes afterwards. And I think probably the same is true for causal reasoning.
Thank you very much for your insights. GB, how's the feeling of both? Yeah.
Yeah, maybe I'll give a comment on my personal favorite definition on reasoning specifically. I think I like to think about reasoning in a more general way than, for example, just math. I like to think of reasoning as anything you can do to improve your performance by spending more, let's say, test time compute. So if I give you more time to think about something, can you do better at any given task? And then what you actually do in it doesn't matter too much. If you do Monte Carlo tree search, or you search the web, or you sit down with pen and paper and try to derive something, I think that's kind of up to you. But if you can demonstrably improve your performance over time by thinking longer, then I think that's reasoning to me. And then causality often ends up playing a role, because it's a very useful framework to think about things and parameterize the world. But maybe it doesn't have to be the only one.
Yeah, thanks for sharing. Now, out of curiosity, I might change the order because I'm highly curious about Swarup's thoughts on what is reasoning.
I believe mathematics is a language to express the causal world we live in, and it's just a form of abstraction. And I also agree that there is this bidirectionality aspect in mathematics which don't hold true in causality. But I feel if mathematics is math AI, especially the benchmarks we have, is one way to understand in an abstract manner how can the models do well on reasoning. And then maybe in future we might have some causality inspired stuff that will help us do well in the math reasoning benchmark. But at this point, I think it's an abstraction, and there is the bidirectionality versus unidirectionality in causality.
Very cool. Thanks for sharing your view. Lastly, we have Tom.
Right. Yeah. It's a great question. Like very, very deep. So I don't know if the mathematical world and the physical world that we use causality to understand are similar or not. It's like an extremely deep question. But I do think they're similar in the sense that we try to understand them in the same way. So the physical world we try to understand with causality a lot of the time. But I think we also think about the mathematical world in causal terms. So we might not always speak like that, but we think of that like the lemmas are causing the theorems and the logical structure causing what theorems are possible in the first place. We might say like, if there weren't infinite prime numbers, then cryptography wouldn't work. So we're like basically considering interventions and like the results of intervention in the mathematical world. Whether that entirely makes sense or not on a fundamental level, I don't know. But like I think about the two worlds in very similar terms.
Yeah, I totally feel you. And also in the specific context of like responding to Tom's comment, because you work a lot on agents, and I wonder maybe causality is more a concept when agents need to interact with each other, understand how the world works. And I'm also really feel it's really lucky that we have the co-authors of the two iClear 2024 honorable mention, one applying GFlowNet to sort of make LLMs understand causal structures better, and Tom, your work on how causality helps agents transfer their knowledge across environments better. Continuing on that line, what do you view is the future role of causality for LM development? Does it sound like we still let the pre-training team do all the existing things that they are trying, and then maybe causality sounded like a lightweight fine-tuning, reinforcement learning thing, or like the other case would be maybe the causality researchers should do interpretability and see how post-hoc LM work. So there are many stages in LM development or understanding. And I wonder people's views. And we might do the reverse order from Tom to Swaroop, maybe GB Swaroop, and Joshua and Benhard.
Right, so that was a whole bunch of questions in there. Yeah, maybe just starting with the paper you mentioned. Just to talking about my own paper. So there we show that if you have an agent that's robust, that can robustly adapt to various changes in the environment, just by observing the behavior of the system and how it adapts, you can actually infer the entire causal structure of the environment that this agent is interacting with. So this is like a mathematical proof that in order to robustly adapt to changes in the environment, you need to know the causal structure of your environment, because you can infer that structure just from the behavior. And to me, this illustrates a little bit how I think causality can be useful. Not the only way it can be useful, but one way it can be useful, because it helps us. It's not just about the agent understanding the world causally, but it's also about us using the theory of causality to understand the agent. And I think this is what this theorem does in a sense. It helps us to understand what are the things that an agent needs to be able to do and have in order to act well in the world. So in particular, it needs a causal model, and this says something about what training data is needed for train robust agents. And I think this is just one example of how causality can help us understand how to build better agents. Yeah.
Great, thank you, Tom. GB?
So if the question is whether we need to infuse more causality in our models, I think at the level of, say, architecture, etc., I think the answer is most likely we don't need to. I think these models are already learning a lot about causality. One reason is because we've pre-trained them. They've read a lot of causality papers that people in this audience have written. They understand these papers, and then we trained with a lot of RL now, and it's going to be more and more RL over time. So they actually interact with the world, and if they make hypotheses, they can test them. They're building their internal models. They're not explicit. We can't really see them, of course, right now. But I don't think we need to. It would be really cool, though, to be able to see them. And I think actually that's the part I'm most excited about, everything in interpretability, figuring out how it is that these models work, where they represent these models internally, what they look like. But I don't think we need to force the causality into the models. I think they're learning it on their own, and it would be nice to be able to tease it apart post hoc.
Very cool. Yes, we have a comment in the middle.
Yeah, I think that there's another option, which is different from the two you suggested, and in which is connected to interpretability, but not in the way of like looking inside the neural activation, but rather asks the model to generate the explanations and the causal structure or parts of the causal structure. So they already do a little bit of that, but I think we could be more formal about it. And of course, in my group, we've been working on generating causal graphs, not using LLMs, but using transformers. And I think in the future, we could imagine that these LLMs are not pre-trained in the current way, but pre-trained in a way that they look for causal explanations for the data that they're trained on, that they're the real data that they're seeing. So it's it would be a different paradigm, and it wouldn't require like trying to put causality inside the neural net, but rather train it in a way that it's forced to think about causality and be explicit about causal structure that it thinks is a good hypothesis for whatever piece of data it sees.
Very cool. Maybe we can have Swaroop and then Benhad.
I think very interesting question and very interesting discussion. See, as a believer of scaling law and a deep learning researcher, I also believe that a lot of things model can learn from data, but then there's a lot of redundancy in terms of parameters, in terms of data, and what can actually produce the right inductive bias that can scale up really well. That is still the key research question. I see that maybe if we can come up with something like GFlowNet and or some of this stuff where you can use causality to probably, I think we can remove this redundancy in the parameter space as well as in the data space. Then I think maybe that will help us as we do inference, like with low inference compute. Maybe we can solve hard math questions, which we are not able to do right now. So I would like to see some of this work, and especially the scaling aspect, if it can scale well in terms of compute and data.
Very cool. So we have diverse views, and Benhad, very looking forward to your thoughts on the topic.
Yeah, so many wise things have been said already. Maybe I can add one aspect, could be less wise, but if I try to sort of go back 5 years in time, if we're honest, I think most of us wouldn't have expected how far we can get with LLMs. Although I do have to admit that Giambattista already as a PhD student, he kept going on about AGI, and I was trying to tell him to do something reasonable. So I think he was an early believer. And I think 5 years ago, there would have been a sort of philosophically quite tenable or maybe even popular or a majority position to say, if we really want systems to learn about causality, they have to be able to interact with the world. And I mean, there are all these old experiments from biology. Even if you don't let animals interact with the world, many things don't develop in the same way. And now we have these systems that do seem to have an astonishing amount of causal knowledge. And I am still grappling with this. And I think I have two ways in which I grapple. So the one way is to try and show that they don't really understand causality. So find ways of systematically testing them. And I think causality, just like mathematics, is a very nice way of systematically probing the knowledge of such systems, because we can generate lots of statements which we know to be causally or mathematically true, and we can test LLMs for that. And CJ, you worked on this kind of problem. And the second point is maybe to try to understand whether there might be ways in which a system that basically learns all the knowledge of the world, all the different distributions, changing distributions, and compactifies it into a finite size model. Maybe such a model is forced to automatically identify causal modules in the data, because those are the ones that are more likely to be robust across problems. So they are more generalizable, even as modules. So it would be very interesting that if, to hypothesize, and we started working on this, that if the scaling laws continue to hold true, maybe at some point there's no way other than actually identifying the correct or useful causal modules underlying the data.
A comment on this. Currently with LLMs, we are confounding two things. One is the knowledge of the causal structure, or in general, not just the structure, but the causal model broadly, and being able to answer questions, because you're basically learning all conditional probabilities, which is inference. And so these two tasks, one, how does the world work on one hand, and what are the consequences of some values of variables on other values of variables, which may not be just ancestors or parents in a causal graph. These are confounded in a typical modern neural net. But there may be an advantage to not confounding them, and the reason is simply that a world model can be exponentially smaller than the say neural net that is required to do inference. It's for almost any probabilistic model, doing inference is exponentially more expensive than what you need to represent the original model itself, like even in a VAE, for example. And so if we can separate these things, we can potentially get much better sample efficiency, because the model itself could be much smaller. Think about like the laws of physics or chemistry. They're very, very small. And of course, inference, so think like running complicated physics simulation, that's expensive. But if you merge the two, then you're going to need a lot of data to learn like end-to-end how to do inference. Whereas you could just use less data and be able to get a better model and then learn the inference by sampling. So in a way, what we're doing right now, when we have a very long chain of thoughts and potentially eventually learning from them, is learning to do inference without having to confront new data, but just having the model be self-consistent, which is what inference is trying to do.
Very interesting. No follow-up on the developer? Yeah.
Can I have a comment? Yeah, I actually agree with what Joshua is mentioning. If we do those, like our inference compute and probably the post-training compute will also go down. And then we can solve these harder problems faster with being sample efficient. But the question I have is, the beauty of like LLMs or like the data-driven models is like minimal human-defined inductive bias, and let it learn from data.
But the causal model could also be learned. It doesn't have to be handcrafted. I mean, that's exactly what I'm talking about. Is not the case where the humans provide the model, but where the model is learned because it's the best model or the best distribution of the models that fits the data.
Yeah, I agree with that. Like if we can find a balance and that can scale well, I think that would be something very interesting.
Although I wonder, a follow-up question on that would be, where do we get the variables, or should the variables be super large?
That's a great question. That's also something you don't want to hard code by hand. And the good thing with LLMs is it's teaching us that there's a very natural way that we can talk about variables in natural language.
Yeah. I wonder if they should be in the size of like millions of variables, or also this like how Sparse autoencoder combination of things.
Exponential number of variables.
Yeah. Sounds great. Cool. So before our exciting AGI question, we will still have one more paper on. Since I know a lot of us have constraints in what we can talk about, let's talk about future tense. In 2025 or 2026, what papers would you look forward to? That can be in the area of further capability. It can be in the area of LLM safety. And then it can come from academia. It can come from industry. What will make you excited?
Personally, I'm especially curious about interpretability. I think on the capability side, my sense is there's already a pretty good recipe that we can keep scaling out for a while. I think one of the main reasons I got into neural networks is I was genuinely curious to understand how minds work. And it feels like now we have really cool artificial minds, and it would be interesting to know how they work. And yeah, we still haven't figured out too much about that.
I want to go back to the interpretability suggestion I made earlier. Like, it'd be great if we could make the neural nets themselves generate their own explanations. But okay, we can already do that, except it's not trustworthy, right? So we need to make sure, for example, that the reasoning chains and the causal explanations that a neural net produces are actually correct, that they satisfy, the laws of probability and logic. And so if we could do that, we could end up with models that are going to be safer because they can be trustworthy. So this question of being self-consistent and consistent with the data. So we already have models that are consistent with the data, but not self-consistent. And this would be really good for safety, but also for like user interfaces, and explainability in general is a very good feature.
Yeah, there's definitely one thing that seems to be happening is that these models already tend to be quite self-consistent on their own. And I think one reason is that it's just helpful for the model to be faithful. Most of the conclusions the models get to are representative of the chains of thought. I think maybe Yosha's main concerns are maybe about what if there's some intent that the user and the models have, etc. And I think those are separate questions.
The reason why people are interested in understanding what is going on inside the networks is that they don't necessarily trust the answers that they're getting. There could be scheming issues that are, beginning to attract attention. And well, what do we do when we get to AGI, right? Where the scheming might be more difficult to trace.
Awesome. We can. Yeah.
I want to see a scaling law paper. Next year or next year, where it can show that if you use a causal inspired model, it's like scales well with respect to compute and solve the question with being sample efficient.
Awesome. So someone looking forward to scaling laws, and two of us looking forward to interpretability a lot. And what are our online panelists thinking about? Maybe Benhard and then Tom?
Yeah, so personally, I'm quite interested in this scaling law question and connecting this to the emergence of causal mechanisms. I mentioned that before, but if I were to express a wish for a paper that somebody else or a system that somebody else could build, then I would say it should be a causal companion for writing clean scientific papers, in the sense that I often work with people in different fields of science, natural science or medicine, and I have the feeling that often when you deal with non-trivial systems that involve interventions, changing distributions, etc., if you look at things in great detail, for instance, you often find potential confounders that people haven't controlled for, and causal errors where people confuse correlation and causation, and this can be arbitrarily subtle. And I think it's just that there's not enough experts to look through all this, and even scientists that are excellent in their respective fields don't have the training in causality. So I think it would be great to have systems that read scientific papers and ask good questions and give suggestions for how to improve the data analysis, how to be careful about the interpretations, because I think so many of the things in the world depend on scientific knowledge and on proper understanding of complex systems and modes of intervention that we have in these systems. So I think there our community could make a difference there.
I totally feel you. So causality augmented scientific assistant, helping us sort of improve our epistemics and the way we understand the world. Great, Tom.
Yeah, great. This is an interesting question. I'm going to try a very ambitious answer. I think we should raise our gaze a little bit. I think currently people are very focused on the actual systems that we build. But I think we should actually bring in the humans into the picture. These systems are becoming extremely influential, are going to become very influential in society in the next few years. And what is it that we want to preserve in that transition of society? I think clearly it's some kind of human flourishing. And I think there is a deep theory waiting to be developed around how human agency and artificial intelligence, artificial agency, how these things should interact properly. It's not an easy question, and I think but I think it's a very important one. Game theory kind of takes a stab at it, but it has like a very abstract perspective what an agent is, and not a very structured take on what kind of environment, what kind of interactions are possible. So I think it's possible to develop a more nuanced theory around what kind of agents are there, what kind of interactions are there, how can one agent make another agent better or not. That's the direction I'm most excited about, and I think Causality can have a big role in articulating that vision.
Very cool. Just to clarify, because there are different connotations on agent, I guess you mean something that's sort of embodied in the real world and can do actions, or?
Yeah, that's a huge question. What is even an agent? I think it's something that a lot of people are talking about, AI systems acting autonomously. But I think humans are also agents, and how can we make humans better agents using AI technology? That's the fundamental question I'm asking.
Very cool. Thank you. And we will use the last 10 minutes diving into different possibilities of AGI and what's the role of causality if that comes. So we have a series of things. The first one is, what's your definition of AGI? And can you talk about that with regard to the current O1 and Gemini AI or other models that we know about? And then where might causality play a role if developers are able to reach AGI? What impact might it have on the world?
I'd like to go if you don't mind, because I think what I want to say connects directly to what Bernard and Tom just talked about. So in terms of AI safety, with respect to AGI or even superhuman whatever, the thing that's most concerning is agency of the AI, in particular if the AI has goals or sub-goals that could be nefarious and that we're not aware of. So that's the scheming thing. And right now we don't know how to deal with that. But I think that there is another path to build machines more like what Bernard was talking about, that could help us advance science, that could help us understand the world. And that's where the connection to causality is, right? So you could imagine future neural nets whose only goal is not to do things in the world or to maximize reward, but just to understand how the world works and build a causal model, or, I think a more plausible thing is a distribution over causal models, because we don't know what is the structure and so on. And so something like this would not really help us to achieve things in the world directly, but indirectly, more like, as Bernard was saying, like really make sense of the scientific literature, make sense of all the data that is available, but trying to explain it through a causal structure. And that would be an amazing tool for scientists. And when people talk about, all the benefits of AGI and so on, they talk about things like advances in medicine or helping us to fight climate change and misery in the world. And a lot of that is just scientific advances. And we don't need agents for that. We could go a long way towards even superhuman understanding of the world without having to build agents that have potentially dangerous goals.
Great.
Yeah, I just want to say I really agree with this.
Oh, go ahead, Tom.
No, just a short remark that this is exactly what I have in mind, where we have AI technology that actually makes us better rather than we just delegate to AI agents. Yeah.
Awesome. I guess some people might have different views.
Okay, maybe let me just start with, yes, the first question was definition of AGI. I'm just
Yes.
going to answer that one and then maybe come back to this. I think, words are just words, so we define them whatever we want. And I think these days I mostly hear three definitions of AGI. One is this maybe also called transformative AI, something that can, for example, completely change the economy. And doesn't necessarily say much about relative to human intelligence, what it can do, what it cannot do. And I think we're definitely pretty close to that. These models are already pretty good. They can automate a lot of activities, improve productivity in different ways. I think the other two definitions are more about human minds. And then I would say, some people say, well, AGI, it's a machine that can do roughly anything the average person can do. And by roughly anything, I mean any interesting task. Of course, we need to clarify the distribution of tasks we care about. And then the other one would be, well, it's as good as the best human at any interesting task. I think right now we're somewhere kind of in between-ish. Like, these models are already much better than most people at most things. And they are vastly better than any person at some things.
Of course, you mean cognitive tasks, right? Because
intellectually, yeah, exactly, yeah. Nothing physical, of course. For example, these models already speak 200, 300 languages, and there's no human being who could ever speak these many languages. And then there's a few things that they're not yet better than the average human, and a few things that are not better than the expert humans. But then it feels like this definition is not necessarily very interesting, because what if it's good at everything except one thing? So you don't call it AGI. What if it's like superhuman at every task except solving Sudokus? Okay, technically it's not AGI. So I don't know. I think these definitions are interesting, but I think the part about impacts is more interesting, and it feels like we're somewhere on that spectrum. The progress is happening there.
If you think about impact, you can think about positive impact, like on the economy, but you should also think about potential negative impact. And in this case, a machine that doesn't need to know everything. It just needs to know enough things to be dangerous, and that's a much more limited set of skills.
Yeah. So, I mean, when I think about the impact, I'm thinking about both positive and negative impacts, of course. I think this thing you were mentioning earlier about we don't have to train them to maximize reward, we should train them to maximize understanding. I think that makes sense to me, but the two things don't have to be in opposition, right? You could say, I can set up my reward to be understanding. For example, in science, you could say a good theory is one that allows me.
I don't think that's the right way to get understanding. Maybe that's the way we have it, but if we want to build machines that are safe, then making them maximize the reward is just begging for trouble.
Maybe I'm curious to hear what you think is a better paradigm then. Because what I'm trying to say is that reinforcement learning,
a better paradigm is to basically fit well the data while having simple theories about it. That's science.
But I mean, who inputs the data? Because one thing scientists do is that they go around and collect new data based on their understanding,
okay,
etc.
so that's interesting. I've been working on experimental design with probabilistic modeling for many years now, and if you have a good causal model, then you can ask all the questions you need to decide what experiments to do. So these are just probabilistic questions. You can calculate things like information gain. So across all the possible exponential number of experiments, how many bits of information will we get? And then you can train another neural net that will sample according to how many bits of information, so you can get to sample experiments you should be doing. So you never need an agent for that. If you have a good probabilistic model and neural nets that can be trained to amortized inference, you can do all these things.
But what if we don't have we don't have good probabilistic or causal models for almost anything, right?
That's what we need to work on, right? That's the whole point of causal modeling.
Yeah. I'm just trying to say, I think that's how one way to build the models is that you let the agent, you let the model do what humans do, which is they interact with the world and they run experiments. What I'm trying to say is that if you set up your reward to be understanding, for example, you say, I'm going to reward you for coming up with models that are predictive. So you come up with a good theory, and then if I test it in for example, auto distribution, it makes good predictions. That means you got good understanding. Here's some reward for you.
It's just much more dangerous. For example, the AI might decide that it wants to know better about the world by doing experiments that we would consider unethical. And maybe it knows that we would consider it unethical, so it would try to sneak, somehow its actions so that we don't notice. It becomes much harder to kind of get rid of these potential problems if you're dealing with an agent trained by reinforcement learning, even if the reward is knowledge. On the way to there, it could do some weird things. Whereas if we go back to the original idea of causal models, of just building a good understanding of the world as not a reward, but the sort of how you train it, I think you can avoid all this.
Yeah, I think I'm just afraid that we won't find the causal models, that we don't have causal models for everything.
Well, science has.
But not for everything, right? I mean, we build science by...
Sure. No, but it doesn't need to be for everything. You can marginalize over things you don't know.
Yeah,
You know?
sort of like I feel it in that there are two different approaches that has been mentioned. Oh, Bernhard, yes, come in.
I just wanted to say I'm much tempted as a non-AGI person. I want to give another definition of AGI. So my definition is AGI is whatever we haven't reached yet. So we will continue to make progress. We can beat the world champion in chess, in Go. We can pass a Turing test. So we'll get better and better, seeking to get closer to a human-like intelligence. But we will continue to find clever ways of finding shortcomings of these systems. We'll continue to move the goalposts and say we're not quite there yet. And then for a while, we will continue to use this mythical notion of AGI. And maybe at some point, we used to call it strong AI, and then people forgot about it. Now we call it AGI. Maybe we will forget about it, and then in 50 years, another term will come up.
But that assumes we never build machines that are smarter than humans. I mean, once we really get to that point, then we can't have your goalpost moving story anymore.
I was trying to be provocative, and I might be wrong. So I shouldn't have said 50 years. I think I should have said 20 years. Let's see.
Well, that's the purpose of this question, to get very diverse views and thoughts. So maybe we have one comment from Tom, and then Swaroop as the concluding view.
Oh, I'm not sure I have too much to add. Great perspectives, but yeah.
Okay, so are you in the Yosha camp or GB camp? Or
No, I'm very much in the Yosha camp. That's right. I think building systems that understand, that model the world is like a great way to complement humans. And I think that's really what we should be looking to do, rather than build AGI agents, which is dangerous. And also, I think we'll take away some of the fun. Like, doing things is actually like part of the fun, and like we shouldn't outsource all the doing.
Great, thank you, Tom. Swaroop?
Yeah, in my personal opinion, like AGI is some model that can do as good as average human in variety of tasks. But then the model, just like an average human, if you change the question slightly or change the language, the human can still answer it correctly. But models, currently, they may not be able to answer if you change the language or rephrase it. The question about rewarding outcome versus rewarding understanding, definitely rewarding understanding. If you have a reliable way to reward the understanding, reward the chain of thought, we should do that. And if it can scale, that would be great. Now coming to average human, when they do different tasks, can they explain everything they do? I'm not sure. But yeah, I think I agree that if we can find out a reliable way to evaluate understanding, to know beforehand if the model is going to have some kind of evil intentions, that would be great.
Can I just add one last thing? I think maybe my sense is we shouldn't be demonizing agency overall. For example, would I want my agents running on my laptop to install my, latest Python update if it stopped working? Probably. That doesn't sound too dangerous. Would I want to give, first proto-AGI the control of all nukes? No, probably not. There's somewhere a line in between, and there are some things that are pretty risky and some things that are not, and my sense is we're trying to build up to something safely, trying to draw the line of, okay, what is the amount of agency we can give to these models such that actually are useful to us and help us understand things, and they themselves learn to be better understanding the world and helping us understand the world without going so far as into going to risk territory by giving it too much agency.
Well,
without
we
knowing.
don't know where the line is.
But you don't want to set it up at don't install my Python 3.11.
Until we're sure that we're not going to create catastrophic outcomes, yes, I think it's better to be safe.
Well, what I'm saying, there's probably some things that
I see the two online participants getting very excited.
So let me just add one example of what Giambattista just explained, which many of us are using, is an airbag in a car. So I'm pretty sure nowadays they don't use just a rule-based system. They probably use some kind of neural network to decide when the airbag fires and when not. And I once talked to an engineer from Bosch, and he said, there's no guarantee that airbags might not sometimes kill people. So it can happen, but they've saved many lives. And over many years of testing and engineering, we have come to trust these systems to autonomously decide when to inflate. And it probably made the world safer. Now that's an extreme example, and there are other extreme examples where we are certainly, I think Giambattista gave such an example, we're certainly not going to give up our control, and all the difficulty is the space in between.
Yeah, what I wanted to add is, I think, yes, in some sense you can maybe build towards a line and build agents up towards that line. But it just seems better to build systems that complement us, and instead of makes us better, then we avoid the dangers and keep the fun.
Yeah, thank you so much, Tom and Bernhard and Yosha, GB, and Swaroop. We have a pretty fun discussion, and all the audience, you have free research ideas from all these great minds. And I also appreciate how we clarify the definition of ideas, and some of us hold different definitions and assumptions, and we lead to different research agenda. And thank you again to everyone, not only the panelists, but all the audience who have been with us for the past 2.5 hours. Yeah, let's keep in contact. Thank you.